Welcome back to Physics 192. I'm Gerard Blanchard. Last time I introduced electrical circuits with batteries and resistors and Kirchhoff's laws, the two starting equations that we're going to always use when we're working with electrical circuits. We did some examples last time. Let's continue with some more examples. Here we have a circuit. Find the current in each branch of the circuit and specify the direction of each. So please draw your circuit. You're going to have to make an assumption about the direction of the currents in each branch. There's going to be three different branches there. So there's going to be three different currents, I1, I2, and I3. You're going to have to make an assumption about the direction that each one runs. If your assumption is wrong, that's okay. You'll just get a negative sign for the current, and you'll know that you should turn the current around in reality. So please get started on that, and I'll give you a few seconds to get ahead of me. Let's draw our circuit. We have a 25 volt battery, and I'll mark the positive side, connected to a 122 ohm resistor. And then I have another resistor, a 5.6 ohm resistor. And then I have another branch of the circuit with a battery with the positive side over here, and it is a 5 volt battery connected to a 75 ohm resistor. And they connect back here. I'll start by assuming that I1 runs like this. Runs out of the positive side of the battery, and then splits up into I2 and I3 like this, so that I1 flows into this point and I2 and I3 flow out, and we have I1 is equal to I2 plus I3. That's one of our equations for our three unknowns. Our other equation is going to, or our other two equations are going to be our loop equation, our voltage loop equation, or delta V total is equal to 0, and we'll have to do that twice. Delta V total is equal to 0. I'll start with this loop right here, go around this way. I'll start from this point that I've already marked, and I will proceed counterclockwise. So first I'm going across the 5.6 ohm resistor in the direction of the current I2, so I'm going downhill or down voltage. So it'd be minus 5.6 I2. And then I'm going once again down voltage, or in the direction of the current, across a 122 ohm resistor, so it'd be minus 122 I1. And then I'm going up voltage, uphill, across the battery, so it'd be plus 25 is equal to 0. And then I'm back where I started. So that's why it's equal to 0, because I'm back where I started. For my second loop, I'll just go this way, and that would be, I'm going up voltage across the 5 volt battery, so it'd be plus 5, and I'm going down current or down voltage, or I'm going with the current or down voltage, so it'd be minus 75 I3, And now, as I go back to my starting point, I'm going across the 5.6 ohm resistor, but I'm going against the current. So I'm going uphill or up voltage. So it'd be plus 5.6 I2. And then I'm back where I started. So that is equal to 0. So my change in voltage as I go around here has to equal 0. So now I have 3 equations and 3 unknowns, so we just solve them using our method of algebra. I'll start by substituting in for I1 right here, and then I'll have an equation with only I2 and I3 in it. So I have negative 5.6 I2 minus 122 times I2 plus I3 plus 25 is equal to 0. That's a 25 right here, same as that one. So now I have minus 5.6 I2, and then I have another negative 122 I2s. So that would be negative 127.6 I2s in total, minus 122 I3s, so minus 122 I3 plus 25 is equal to 0. So as I said, you can see that I have 2 equations now, here and here, with 2 unknowns in them, I2 and I3. So what I will do now is I will solve this equation for one or the other. Let's say I'll solve it for I3 by adding I3 to both sides. I'm sorry, adding 122 I3s to both sides. So I have minus 127.6 I2 plus 25 is equal to 122 I3, or negative 127.6 I2 plus 25, all divided by 122 is equal to I3. So now I have here something that is equal to I3, and I can take this and substitute it in for my I3 right here. Let's go ahead and do that. I have 5 minus 75 times I3, which would be negative 127.6 I2 plus 25 divided by 122 plus 5.6 I2 is equal to 0. So let's see what I have here. I have negative 75 times negative 127 divided by 122 I2s from this term. And then I have another 5.6 I2s from here. So let's figure out how many I2s we have in total. So that would be negative 75. I'll go ahead and calculate that. Negative 75 times negative 127.6 divided by 122 plus 5.6. And that gives me 84 I2s. 84.0. So 84.0 I2. And let me just double check my calculation there. I have negative 75 times negative 127.6 divided by 122 plus 5.6, and I get 84.0 I2. And what do I have for my numbers? I've got a 5 right here, and then I've got a minus 75 times 25 divided by 122. So let's go ahead and calculate that. I have 5 minus 75 times 25 divided by 122. And that gives me a minus 10.4. That's equal to 0. So 84.0 I2 is equal to 10.4, or I2 is equal to 10.4 divided by 84.0, or I2 is equal to 10.4 divided by 84. And that would be 0.124 basic metric units of current, which are amperes. And I'll point out that I get a positive value for I2, which means that the direction that I assumed for I2 was correct. If I just made an assumption here. I assumed the direction that these currents would be flowing, and if I were mistaken, then that would be okay. What would happen, though, is that I would get a negative number for I2. But in fact, I got a positive number, which means that I2 is indeed flowing from left to right. Now that I have a value for I2, I can go ahead and substitute it in here and figure out I3. And so that would be negative 127.6 times 0.124 plus 25, all divided by 122, is equal to I3. And what is that? Negative 127.6 times 0.124 plus 25. And I have to make sure to put all this in parentheses so that I'm dividing everything by 122. And I get 0.0752 amperes is equal to I3. It's also a positive number, so I did choose the direction of I3 correctly. And finally, for I1 is equal to I2 plus I3, so that's 0.124 plus 0.0752, or I1 is equal to 0.124 plus 0.0752. And that is equal to 0.199 amperes. And it's also positive, so I did, in fact, assume the direction of I1 correctly as well. So I've got all of our currents now, and we have the correct direction. So the currents are indeed as they were assumed to be. I1 is 0.199 amperes, I2 0.124 amperes, and I3 0.0752 amperes. Let's work another example. Find the unknown EMF and the unknown resistor in the circuit below. So you have a circuit diagram where you're given the current in two branches of the circuit. You have a battery with an unknown EMF, that's the one all the way to the left, and you have a resistor of unknown resistance, that's the one all the way to the right, and you're asked to find the unknown EMF and the unknown resistance, but you'll do it exactly the same way. You'll use your Kirchhoff's laws as your starting equations to answer this question. So draw your diagram, use your Kirchhoff's laws, and please answer the question. Okay, let me draw the circuit. Draw that line across the top. And then we have a resistor and a battery. And the resistor has 6 ohms. The positive side of the battery is here. It has an EMF of E. We don't know what that is. We have a resistor and a battery in the middle. The battery has an EMF of 125 volts, and the resistor has a resistance of 4 ohms. And then finally we have another resistor over here of unknown resistance, and so I'll call that R, and that's what we're looking for. And we're also looking for the EMF over here. We are given the current in 2 branches of the circuit. This is 1 ampere. This is 10 amperes. And they both flow into this point right here. So we can actually very easily calculate the current through this branch. I'll call it I. It's also unknown, but we know that from Kirchhoff's law, this current plus this current have to equal this current. So 1 plus 10 is equal to I. So we know that I is equal to 11 amperes. So the current in the middle is 11 amperes. We still have 2 unknowns, E and R. So we'll have to use our Kirchhoff's voltage law twice. And so I'll start from this point right here, and one time I'll go around this way, and one time I'll go around this way. So delta V total is equal to 0. Delta V total is equal to 0. I'll start from here and I'll go around clockwise. So I'm going down current, and that would be 4 times I, or I'm sorry, minus 4 times I, because from here I'm going with the current, so I'm going downhill or down voltage, so it'd be minus R times I, or I times R. So it'd be minus 4 times 11. And then I'm going across this battery in the up voltage direction, so that would be plus 125. And now I'm going to turn this way. I'm going across this battery in the down voltage direction, so that'd be minus E. And then I'm going across this resistor with the current, or down voltage, so minus 6 times the current, which is 1, and all of that has to equal 0. And I have an equation with nothing but E in it, so I can go ahead and calculate. Let's see, this would be minus 44 plus 125 minus 6. And then I'm going to add E to both sides, and I'll just have equals E, or minus 44 plus 125 minus 6 equals 75. So 75 volts is equal to E. So we've answered one of the questions, what is the unknown EMF? For the second one, I'll go around this loop this way. So once again, I'm going with the current, or down voltage, so minus 4 times 11. Going up voltage across the battery, plus 125. Then I'm going with the current across this resistor, or down voltage, so minus 10R. And I'm back where I started, equals 0. So I have minus 44 plus 125, and I'll add 10R to both sides, equals 10R, or minus 44 plus 125 divided by 10 is equal to R. So I have the quantity minus 44 plus 125 divided by 10 equals 8.1. 8.1 is equal to R. And so we've figured everything we can about the circuit. We figured out the unknown current, even though we weren't asked for it. We figured out the unknown EMF, and we figured out the unknown resistance of 8.1 ohms. Let's work one more example. This is going to be a long one because it's going to have a lot of unknowns in it. It's going to have a lot of branches in the circuit, but we're going to approach it systematically using our Kirchhoff's laws as our starting equations. A 24-volt EMF is connected to the terminals A and B in the circuit below. What is the current in the leftmost 4 ohm resistor? So the leftmost 4 ohm resistor. Go ahead and draw your diagram and think about your approach to this question. Let's draw the circuit. I'll start with our battery. And I'll put the positive terminal up. And it is a 24-volt battery. And then I have a resistor, and then another resistor, and then another resistor, and another resistor, and then I go down with another resistor, and then in between I have a resistor, a resistor, and a resistor. I have no resistor here, but I do have a resistor in here, no resistor in here, and I have a resistor right here. Okay, and let's see. This is 1 ohm, 1 ohm, 3 ohms, 2 ohms, 4 ohms, and this is the current that we're interested in. 4 ohms, 6 ohms, 4 ohms, 2 ohms, and 3 ohms, and 1 ohm. Okay, and I will start with this current here. We'll call it I1. This current that we're looking for is I2, and that's what we're looking for. And then I have I3, I4, and then this current is going to be the same as I3, because whatever flows through all of this, I3 comes into this point and it all flows this way, but it's got to come back to give me I3 again. And then I have I5, and this is going to be I5 again. I6, and then finally I7. So we actually have 7 unknowns. We have 7 unknown currents here, and we're looking for this one right here. We're going to have current law equations at those 3 points. So specifically, I5 is equal to I6 plus I7, and I3 is equal to I5 plus I4. I3 is I5 plus I4. I5 is I6 plus I7. And I1 is equal to I2 plus I3. And then we're going to, that gives us 3 equations. So we're going to have to use our Kirchhoff's voltage law 4 times. And what I'm going to do is I'm going to go once around this loop, once around this loop, once around this loop, and then finally around this loop. And that way we're going to be eliminating unknowns as we go from right to left until finally we're going to be left with an equation with just I2 in it. Okay, let's do that. If I go around this loop right here, then I have, well, minus 2I7 minus 2I7. So that would be, well, I'll go ahead and write delta V total is equal to 0. Be minus 2I7 minus 2I7. And then I'm going against the current here, so plus 4I6 equals 0. So I have minus 4I7 plus 4I6 is equal to 0. I will add 4I7 to both sides, and I have 4I6 is equal to 4I7, or I6 is equal to I7. And that's all we're really going to need to know. We don't need to know what I6 and I7 are, but this relationship is what's going to help us as we move from right to left across the circuit, because we know that I5 is equal to I6 plus I7. I'll go ahead and I'll rewrite that here. I5 is equal to I6 plus I7, or I5 is equal to I6 plus I6, or I5 is equal to 2I6. So now we've eliminated I7, and then we'll be able to go around this loop, ultimately eliminating I6, and so on. Okay. Let me go around this loop right here. I'll start from this point. I'm going across this resistor in the direction of the current. So let me write delta V total is equal to 0. So that would be minus 3I5. Minus 3I5 minus 4I6 and then minus 1I5. And I'm just going to write minus I5. And then plus 6I4. And I'm back where I started, so that equals 0. Let me double check that. Minus 3I5 minus 4I6 minus 1I5 plus I4 is equal to 0. And so I have minus 3I5 and minus I5. That's minus 4I5. And I've got minus 4I6, but I know that I6, actually let me carry this one step further. I6 is equal to 1/2 of I5. So for I6, I can substitute in 1/2 of I5, so minus 4 times 1/2 I5 plus 6I4 is equal to 0. And so that would be minus 4I5 minus 1/2 of 4I5. So that would be minus 4I5 minus 2I5. So it would be minus 6I5 plus 6I4 is equal to 0. Or 6I4 is equal to 6I5, or I4 is equal to I5. So I4 and I5 are equal. And then from that, I can bring in this equation right here. I3 is equal to I5 plus I4, or I3 is equal to 2I4, or 1/2 I3 is equal to I4. And we're going to repeat this for our next loop. So let's carry it on for this loop right here. And I'm going to have to move my diagram off the screen. I'm sorry. Delta V total is equal to 0. I'm going to go around the top loop. Here, I'll say it out loud. And I'll have negative I3, negative 1I3, minus 6I4, plus 4I2 equals 0. So it would be negative 1 times I3 minus 6I4 plus 4I2 is equal to 0, or negative I3 minus 6 times 1/2 of I3 plus 4I2 is equal to 0, where I've used that I4 is 1/2 of I3. And so that would be negative I3 minus 3I3, so that would be minus 4I3 plus 4I2 is equal to 0, or we know what that's going to come out to be. That's going to come out to be I2 is equal to I3. And we're going to use our last current equation right here. I1 is equal to I2 plus I3, or I2 is equal to I3, I1 is equal to I2 plus I3, or I1 is equal to I2 plus I2, or I1 is equal to 2I2, which gives us 1/2 I1 is equal to I2. And now it's time to do our loop, do our final loop around this part of the circuit right here, which is going to give us our I2, which we're looking for. Okay, I'll say it out loud. What we're going to get? We're going to get negative 4I2 minus 3I1 plus 24 minus 1I1 equals 0. So we do that again. Delta V total is equal to 0. So it would be minus 4I2 minus 3I1 plus 24 minus I1 is equal to 0. And now you see I have an equation with nothing but I1 and I2 in it. Actually, I'm not going to use this substitution. I'm going to use this substitution because that way I'll have an equation with nothing but I2 in it. So I have minus 4I2 minus 3I1, which is 2I2, plus 24 minus 2I2 equals 0. Let me add up all of my I2s. I have 4 here, 6 here, and 2 here, and they're all negative. I have negative 4, negative 6, and negative 2. So it's going to be 4 and 6 is 10, so 12. Negative 12 I2 plus 24 is equal to 0, or 24 is equal to 12 I2, or 24 divided by 12 is equal to I2, or 2 amperes is equal to I2. And that is what we were looking for. I2 is 2 amperes. So the current going down through this resistor right here is 2 amperes. That's what we were asked for. But if we wanted to, we could go back and we could figure out all the rest of the currents as well. Finally, let me introduce the concept of electrical power. Resistors always dissipate electrical energy. They convert it to heat. A discharging battery, meaning that current flows from the positive to the negative terminals of the battery, supplies energy to an electrical circuit. A charging battery is receiving energy from an electrical circuit. So if you have a current flowing into the positive terminal of a battery, then you're actually charging that battery. Other devices, such as motors, convert electrical energy into work. In every case, the rate of energy supply, dissipation, or work, meaning the joules of energy supplied or the joules of heat created or the joules of work done per second, the rate, energy over time, is the power of the circuit, and power is equal to current times the change in voltage. So electrical power, P, capital P, is equal to electrical current times the change in voltage across which that current flows. So if current flows from high voltage to low voltage, then work is being done and electrical energy is being converted to some other form. It's either being converted to work or it's being converted to heat or something like that. The important equation here is the one that relates current, voltage, and power, and that is power is equal to current times voltage. Remember that electrical energy is equal to charge times voltage. So when an electric charge is at a high voltage, it has high electrical potential energy, and when that charge moves to low voltage, it moves to a low electrical potential energy, so it's lost energy. Now the rate at which current flows is the current, so the rate at which charges are losing energy is equal to current times voltage. Energy is charge times voltage. The rate at which energy is being lost, which is the power, is equal to current times voltage. So that's our important equation that we're going to use quite a lot from here on out. Electrical power is equal to current times change in voltage. Now remember from General Physics 1 that power is change in energy over change in time, or power is work done over change in time, or the rate at which work is done or the rate at which energy is converted. So often your questions might ask about work done or energy lost. Remember that when we're talking about a rate of work or a rate of energy exchange, then we're talking about power. So power is the rate at which energy is converted or work is done or energy is lost. That's from General Physics 1. What we're introducing here that's new is the electrical power, which is current times change in voltage. We'll do some examples of using electrical power next time. Until then, think physics.